Good morning, everyone. Good morning. I'm excited to welcome you to the second lecture in our Saturday Physics for Everyone series this fall semester. It's great to be doing this again in person, and it's another exciting year for us because this is actually our 30th anniversary of the Saturday Physics for Everyone program. So, next event, which is on October 28th, just as a reminder to put on your calendars if you're interested, will be our 30th anniversary celebration, and we'll be having some open house events. So check out for some emails from me and keep that date in mind as well, too. So for those of you joining for the first time, I'll give you a quick introduction of myself as well as the program. My name's Irene Lira-Ansager, and I'm the coordinator of undergraduate recruiting, research, and placement here in the physics department. So I get to work with prospective students who are interested in becoming physics majors, as well as our students in the department who are interested in doing research and thinking about what they want to do after they graduate as well. And so the program itself, as I said, it's in our 30th year now, and the goal is to be able to share the work that we do in the physics community with you, our community as well, and also give an opportunity for students to learn about what you might be able to do with a physics degree, what research you could be pursuing in your future too. So with that, I will introduce our speaker for today. Cristian Proistosescu is an assistant professor in the Department of Atmospheric Sciences and the Department of Earth Sciences and Environmental Change, having joined in January of 2020. Cristian's main focus is on Earth's climate sensitivity, the amount by which the Earth's surface temperature will change in response to a doubling of atmospheric carbon dioxide. More specifically, he is interested in how climate sensitivity depends on the interplay between spatial patterns of surface temperature and the amount of energy that the Earth radiates to space. Cristian, or Cristi, as everyone calls him, grew up in Romania, where people have just as much trouble pronouncing his last name as everywhere else. His hometown lies in the shadow of the Carpathian Mountains, about 24 miles from the castle of Vlad the Impaler, actually known as Dracula. Between hikes in the southern Carpathians and river trips on the Danube Delta, with friends and family, he developed an early love for the outdoors and the environment. Later on, he developed a passion for physics and mathematics, successfully representing his country at 2 international physics Olympiads. After high school, Cristi moved to the United States to pursue a degree in physics and applied mathematics from Princeton University. It was there that he started pairing his 2 big passions, by exploring several research areas in geophysics, such as analyzing numerical models of ocean currents, doing field work on tidal channels in the Bahamas, and developing statistical models to examine whether changes in the Earth's orbit could have influenced past climate. He continued his education with a PhD in earth sciences from Harvard University. Here, his interests again wandered around between studying the nature of daily temperature extremes to studying the relationship between mid-ocean ridge volcanism, sea level, and carbon dioxide before focusing on estimating climate sensitivity. Since then, Cristi has been working on improving these estimates by combining information from historical changes in climate, numerical simulations, and mathematical models. Cristi's main hobbies are highly stereotypical of Earth scientists. He enjoys hiking, skiing, and the great outdoors. He also tries to find time to spend time with old family, friends, and last but not least, his wife and daughter. Please join me in welcoming Cristi.
Hello, everybody. Can people in the back hear me? Turn it up a little bit. Okay. Or move it up higher. Is this good? Okay. Thank you so much for giving me the opportunity to talk to you today about some of the work that our group does on the physics of climate change, and also primarily some broader aspects about what we know about the physics of climate change, what we don't know, and sort of how we go about knowing more. Before this, I've put up this little quiz, so you can go to slido.com on your phones, type in that code, and you can answer this question. We have 11 answers, so we're going to go from here. So what came first in our knowledge? Did we first observe temperatures going up? Did we first observe atmospheric carbon dioxide going up? Did we first observe the impacts of climate change? Or did we understand all along that carbon dioxide leads to global warming? I'm going to answer this. The first part of my talk is basically going to be answering this question, and I like this distribution because it sort of says, right, the history of this is not well known, is not well understood by everybody. So that's going to be the first part of my talk, what we've already known and how long have we known it. So if I can find my mouse cursor, here we go. We can start with the lecture proper. So the title that I gave Irene was Climate Change 101 from Basic Physics to Global Policy. I chose this title because I wanted people that saw it to have an idea of what I'm going to talk about. But the real title of my lecture, the title of my book, if I ever write one, is going to be Chronicle of a Catastrophe Foretold. And this is really what climate change is. Climate change is a catastrophe foretold. What do I mean by that? Well, the way most knowledge accumulation proceeds, in physics at least, and probably most other sciences, is we have observations that we try to understand. We come up with explanations for that observations. We build theories to explain them. We test those theories, and we slowly refine our understanding and our explanation of the observed phenomena. That's how most science proceeds. And if you look at the debates around climate change and global warming, this is the way these debates proceeded. Back in the 90s, the big debates were about whether or not climate is changing, right? So there were the deniers would say, well, climate isn't actually changing. They were debating the observations. We have these observations that show temperatures are going up, but they come from weather stations that were placed 100 years ago in a field, and now there's an airport or a city around that. There's concrete that heats up, so really we're not seeing Earth's temperature going up, we're just seeing problems with our measurements. And that was the big debate in the 90s, when we first started observing a change in Earth's temperature. Then in the 2000s, once the signal was kind of incontrovertible, there was clearly a signal that Earth's temperature was going up, the arguments against it was, okay, so maybe temperature is changing, but we don't know humans are causing it. Maybe it's volcanoes, maybe it's changes in Earth's orbit, maybe it's just natural fluctuations in a very complex, nonlinear, chaotic, dynamical system. So we've moved on from debating the observations to debating the explanation in the 2000s. By the 2010s, which is about when I got into the field, or when I started getting into the field, when I started my PhD in climate science, the debates have sort of moved on. It was kind of hard to be a serious scientist, or to claim to be a serious scientist and still debate the fundamental theory of carbon dioxide and the greenhouse effect. People were still doing it, people are still doing it now, but by and large the debates had moved on to, okay, maybe humans do contribute to it, but climate change will be small, the effects will be small. So now we're debating the details. Just how big is climate sensitivity? Maybe it's only half a degree instead of what scientists claim it's 3 degrees. So we're now debating the details, right? So it sort of seems to have proceeded along the usual track of you have an observation, you make an explanation, and then you refine the explanation and test your theories. By the way, I should say that we've moved on from that as well. You can kind of tell by who gets invited to argue against climate change in congressional hearings. It used to be statisticians in the 90s, then physicists who are saying it's not humans. Now it's economists and social scientists from certain think tanks who say, okay, climate is changing, humans are causing it. We can no longer reasonably argue against that. But for several reasons, we can't act because it's too expensive, or we shouldn't act because the consequences aren't going to be that big. So now we're moved on to debating what to do. So this is the narrative, and this is the way the climate debate has sort of proceeded. Again, in line with the way we usually accumulate knowledge about a topic. When I say usual, I mean, most of the topics. Sometimes it goes the other way, but that's actually pretty rare. Sometimes we have a theory before we have the observations, and we make a prediction that at the time has really no observational basis, and then we finally make an observation, and usually we get a Nobel Prize if we do that. There's only a couple of famous examples. Einstein's first special theory of relativity was actually based on the observations that the equations for electromagnetism were inconsistent with Galilean transformations and a couple of other observations. But then general relativity was a theoretical breakthrough, and it was really only observationally proven later. Dirac's prediction of the positron, the Higgs boson was another theoretical prediction of the Standard Model that wasn't observed until much later because we didn't have the experimental facilities. Right? It turns out it's difficult to make predictions, especially about the future. It's much easier to find an explanation for an observation. But if you make a theory before an observation and then it comes through, that's usually a pretty strong evidence in support of your theory. And this is actually how climate science proceeded. I think my drink is blocking the radio signal from my slide advancer. And speaking of radio signals, you all have cell phones, or I assume most of you have cell phones. The way cell phones communicate with each other is based on signal processing. It's pretty amazing, right? The guy that first built the theory for this was a pretty smart dude. His name was Joseph Fourier. He was, amongst other things, an officer in Napoleon's army. And he had 2 contributions. One was to signal processing and Fourier analysis. The other one, which was in support of that, was a theory of heat. And in 1824, he writes this paper, general remarks on the Earth's temperature and other planets. This is in 1824. Basically, what Fourier notices is that the Earth's night side is not as cold as it should be. The Earth's day is it gets heated up by the sun, but the nights, according to his calculations of Newtonian cooling, it really should be much colder at night. Why aren't nights cooling more? He thinks about it and he posits that, well, the only reason for that is if there is something preventing the Earth from cooling efficiently. And he posits the existence of a greenhouse effect. So 1824 is when Fourier understood that the Earth must have a greenhouse effect. He didn't really know what caused that. That came a bit later. Eunice Foote in 1856, on the heat in the sun's ray, circumstances affecting the heat of the sun's rays, realizes that actually carbon dioxide is able to trap heat in Earth's atmosphere. And by heat, what I really mean is infrared radiation, which is what the Earth emits and how the Earth cools itself. She has observational evidence that CO2 is a greenhouse gas, and I've extracted this quotation from her paper. If, as some suppose, at one period in its history, the air had mixed with a larger proportion of carbon dioxide than at present, an increased temperature must have necessarily resulted. She's talking about the geological past in this case, but this is essentially a statement that increases in greenhouse gases will lead to increases in Earth's temperature. This is probably the earliest statement of this fact, and it comes from 1856, more than 150 years ago. There's a couple more advances in between. John Tyndall makes more refined observations of CO2. And then there's this guy, Svante Arrhenius, 1896. He's a Nobel laureate in chemistry who was interested in carbonic acid, which is what they called CO2. And he writes this paper, and I've pulled a couple of quotations from this paper. At this point, he actually makes quantitative estimates of how much infrared radiation carbon dioxide would emit and what would happen if we change carbon dioxide. And he puts up this sentence. Any doubling of the percentage of carbon dioxide in the air would raise the temperature of Earth's surface by 4 degrees. These are degrees Celsius or centigrade. That is, 7.5 degrees Fahrenheit, I think. So this is now not just a statement that CO2 causes global warming, but an actual numerical estimation, which holds surprisingly well to today. You know, ballpark. We're physicists. We average everything to the nearest order of magnitude, and in that sense, it's correct. Right? So 1896 is sort of the first actual prediction of global warming. He then says this: the percentage of carbon dioxide in the atmosphere may, by the advances of industry, be changed to a noticeable degree in the course of a few centuries. So he also realizes that the Industrial Revolution is leading to more carbon dioxide emissions, which is going to lead to an increase in carbon dioxide and therefore a global warming. He's living in what is the second industrial revolution. The picture is from northern Germany. He's living in Scandinavia. So he views this as a good thing. By the influence of increasing percentage of carbon dioxide, we may hope to enjoy ages with more equable and better climate. Ages when the earth will bring forth much more abundant crops than at present for the benefit of rapidly propagating mankind. Right? So not everybody thought this was bad. If you live in Scandinavia in the 1890s, a bit of warming might sound like a good thing. So that's sort of the old history of climate change. Right, so timeline. 1824, Fourier posits a greenhouse effect. 1856, Eunice Foote realizes that CO2 is causing that greenhouse effect. 1896, Svante Arrhenius makes a prediction of global warming under CO2 increases. You can actually find a piece of news from the time, coal consumption affecting climate. This is actually an interesting numerical prediction. The furnaces of the world are now burning 2 million tons of coal a year. This adds about 7 million tons of carbon dioxide to the atmosphere yearly. This tends to make the air more effective blanket for the Earth, and the effect may be considerable in a few centuries. Right? So just like Arrhenius, this is based on Arrhenius' work, they thought it was going to take centuries before we notice this. Okay, so we're going to skip ahead. We're going to skip ahead to 1961. 1961, Charles Keeling, University of Illinois, class of 48, hail to the orange. He is an alum of the chemistry department, and he makes the first measurements of atmospheric carbon dioxide. He sets up a measurement station on the top of a volcano in Hawaii. There's not much industry around. It's a fairly pristine place where he can measure atmospheric CO2, and he creates what is now known as the Keeling curve, arguably one of the most iconic data sets in climate science. And he notices within a few years already that carbon dioxide is going up. It's no longer the 1890s when it's only England and northern Germany that are industrialized. This is past World War II now. We are burning a lot more fossil fuels than we were half a century ago. So Keeling's work shows that actually we're already changing atmospheric carbon dioxide considerably. Anybody that was familiar with Arrhenius's work earlier realizes that this has implications. Right? So then we get to Manabe. Manabe, one of the 2021 Nobel laureates in physics, in 1967 writes the seminal paper with a fairly boring title, Thermal Equilibrium of the Atmosphere with a Given Distribution of Relative Humidity. This is basically the physical setup that he uses, but this is the money quote. According to our estimate of doubling of CO2 content in the atmosphere has the effect of raising the temperature of the atmosphere by about 2 degrees. This is similar to Arrhenius, but now this is an actual full-blown physical theory with different spectral bands, accounting for humidity, accounting for everything else. This model is the fruit fly of climate science. This is sort of the fundamental, the simple harmonic oscillator of basic physics. This is the starting point from which we essentially build all of our understanding of climate science. So he won the Nobel Prize for this. We're still in the 1960s. There's still no real noticeable observation of climate change at this point. We have sort of noticed carbon dioxide going up a little bit, but because of all of the weather noise, we haven't really observed temperature change. There's a couple more predictions that follow in somewhat rapid succession. Wally Broker coins the term global warming in this paper. Are we on the brink of a pronounced global warming? I'm going to put the abstract up because it's interesting. A strong case can be made that the present cooling trend will, within a decade or so, give way to a pronounced warming induced by carbon dioxide. Not only was there no observation of global warming, but the Earth was cooling at the time. It's a pretty bold prediction to say, actually, this is going to reverse and it's going to start warming because of carbon dioxide. This is one, I've pulled up 2 more quotes. The natural climatic cooling has compensated for the carbon dioxide, but that will soon bottom out. And again, he says that by early next century, which is now, that's when we are, early next century, we will have driven the mean planetary temperature beyond the limits experienced in the last 1,000 years. There was a paper a few months ago that actually showed that we've now pushed it beyond the limits of the last 1,000,000 years, or sorry, the last 100,000 years. So he was right on the money. Early next century, we will have observed a temperature change that sort of takes us outside of the previous range. There's a couple more predictions that are made around the same time. Jim Hansen is leading a NASA group that makes some more quantitative predictions in 1981. He was famous for giving the first big congressional testimony on climate change in 1988. And then there's this one, which I think is worth highlighting. This is from a memo from 1982 that was not publicly available until very recently. And I've pulled a couple of quotes. The first one, the carbon dioxide content of the atmosphere is of concern since it can affect global climate. Our best estimate is that doubling of the current concentration could increase average global temperatures by 1.3 to 3.1 degrees Celsius, and there is currently no clear evidence that the Earth is warming. This is just a theory, but we're pretty confident in it. And if the Earth is warming, we're not likely to detect it before 1995. Again, right on the money. There was a UN report in 1995 that said that a fingerprint of human-caused global warming is now detectable in the observations. I'm going to highlight one more thing out of this. This material has been given wide circulation to the entity. Management is intended to familiarize personnel with the subject. It should be restricted to the entity's personnel and not distributed externally. Anybody care to guess who was making these confident statements about the effects of carbon dioxide, the magnitude of global warming, and when we would detect it? Exxon. This is an internal memo from Exxon Research and Engineering Company. It's not all secret. Any of you familiar with the big book Numerical Recipes? Okay, well, one of the authors of that book was working for Exxon and was actually making peer-reviewed public manuscripts where they were estimating the amount of global warming. So once they figured out that this is serious, they kind of closed the book on it and decided to go another direction. You can actually go into that memo and you can look at figure 3. I'm going to show a better version of this. This is from the actual memo. They were making predictions of atmospheric carbon dioxide concentration and temperature increase as a function of time. And then you can go and see how well those predictions held up. So, to summarize the timeline of climate science, we've known about the greenhouse effect and the effects of CO2 since the 1800s. By the second half of the 20th century, people like Keeling were noticing that we're increasing carbon dioxide, and then people like Suki Manabe were putting the first coherent physical models of Earth's climate. And then by the late 1970s, early 1980s, we have quantitative predictions of global warming at least a decade before there were any clear, statistically significant, is what we would call them, observations. I'm going to show you why I call this chronicle of a catastrophe foretold. This is a figure that shows temperature anomalies. So this basically means how much has the Earth warmed since about the Industrial Revolution as a function of time. These are the observations of temperature anomaly as they stood in about 1980. So there's a lot of variations, there's a lot of fluctuations, there's a lot of essentially weather. Some volcanoes in there, some dust from the war, some early emissions of carbon dioxide. It's maybe going up a little bit, but it's still too noisy to really say that the Earth has warmed considerably. And this is the point where these people make their predictions. This is what these predictions would have looked like in 1980. This is Wally Broker's curve. This is Jim Hansen's prediction. This is Exxon's prediction for what would happen in 2020. That was made in 1982. As you can see, they're sort of wild, out-of-sample predictions. They predict nothing like anything that has been observed in the past. This is what sort of really makes it a classic Popperian prediction. It's very falsifiable. If the Earth's temperature would have actually continued to stay around the same, then these theories would have been, false. And there's actually a couple of other papers from people that were saying climate change isn't real that do make predictions that this was going to stay flat. This is what actually happened. I've always dared any economist I know to show me an economic prediction from 1980, 40 years into the future, that had this level of accuracy. I'm yet to receive a satisfying answer. It actually is beyond that. This is from another Suki Manabe paper from 1980. this is now a prediction not just of global warming, but of the regional patterns of climate change. So by this point, the climate models are more refined, although still pretty coarse. This is a map of the Earth. In case it wasn't clear to people, this is South America, this is North America, this is Africa. It's like computer games from the 80s. It's like Atari, right? It's extremely, extremely blocky. The resolution is very, very poor. But what this is predicting is there's going to be a lot more warming in the Arctic than anywhere else. So now we're getting into more refined predictions. There's a couple of other what we would call fingerprints, which is that if you look vertically in the atmosphere, the upper atmosphere, the upper part of the lower atmosphere is going to warm, and then needs to go in the stratosphere is going to cool. The second part of the Nobel Prize in Physics in 2021 was given to this guy Klaus Hasselmann, who amongst other things basically laid out the observational framework for how would we be able to figure out if this is man-made global warming. You can think of Tsuki as Higgs with the theory, and Hasselmann is sort of like, this is how we would build a detector to actually detect the Higgs boson. So this is what the predictions look like. This is one part of that fingerprint. The Arctic is going to warm more than the rest. This is what the observations by the end of the 1990s looked like. They're spotty. We don't have observations everywhere. They're noisier. But by and large, they match pretty well. There's more warming in the Arctic. There's also more warming on the continents. North America, Eurasia warms more than the North Atlantic and the North Pacific. So even if you go into some detail, this really is a catastrophe foretold. We've known this for over 150 years. And I really like to get that message out, because this is not how the debate proceeded in the public view. Okay, so this is the timeline again, and I want to make one key point from this part of the talk, which is that if we wanted to stop global warming, we know what we have to do. And we've known since at least 1896, or if you want to argue that Arrhenius' model was too simplistic, we've definitely known since 1967. And really what we need to do is we need to stop emitting greenhouse gases. It's as simple as that. Earth's temperature is a linear function of the cumulative amount of CO2. The more carbon dioxide, the total amount of carbon dioxide we emit sets Earth's temperature.
Is it reversible?
No, but, well, not easily. But it's sort of, for a while we were wondering if there's warming in the pipeline. Like if we stop emitting CO2, will the inertia of the climate system lead to continuous warming? It turns out, luckily, that's not the case. That's been one of the few pieces of good news and real new science from sort of the last round of UN assessments, is that we're now pretty confident that the inertia in the system is pretty small due to some serendipitous compensation effects that I really don't have time to go into. My point is, I shouldn't have a job. We've known this for a long time. So why do I have a job, and what do I do? The details matter. This is what the predictions in the 1980s look like. Okay, more warming over North America. That's good. If you're a disaster, if you're FEMA, that doesn't help you much. If you're FEMA, you want to know at the specific location how is risk going to increase. You might want to know how precipitation is going to increase. And I'm being a bit facetious, I'm showing temperature. Predictions for precipitation were all over the place and are still kind of all over the place. The details really matter. One of the things that we really didn't know until very, very recently is what happens with wildfires. Because wildfires depend on all sorts of things, depend on precipitation, depend on humidity, depend on temperature. Overall, the amount of water vapor in the atmosphere increases, so you might think that's good. That's going to lead to fewer wildfires. At the same time, the amount of thirst, the amount of water that air can hold also increases, so it can suck up air from the soil more easily. It's complicated, is basically my point. And we didn't really have, and we still don't have good predictions of how climate change affects wildfire conditions. This is not a storm cloud. This is what we would call a pyrocumulonimbus. A cumulonimbus is a storm cloud. A pyrocumulonimbus is a storm caused by wildfires. This is from British Columbia from about a month ago. This is a photo of my uncle driving away from wildfires in Kelowna, British Columbia. This is at 2 a.m. They were trying to get out from the wildfires with my cousin and her 3-month-old baby. The wildfires descended on the town within a few hours. Their house was luckily spared. About a third of the town burnt down. And we couldn't really predict this. Our models are still not quite good enough to be able to inform exactly how much wildfire risk is gonna go in different directions. The details matter, and when I say details, these are life and death decisions that planners have to make. And this is sort of where a lot of our work comes in. This is another picture from wildfires in Hawaii this summer. At this point, actually, this is one of the places where sort of data has actually overtaken theory. Now we're looking at data and saying, actually, yeah, wildfires have been increasing due to climate change, and we need to build better theories and better models for how climate change impacts wildfires. Right? So the details matter. If we were to stop global warming, we know what we have to do, but we haven't. Climate change is happening. It's going to continue to happen for at least another couple of decades while we get our together. So we need to understand what the impacts are going to be. And this is sort of what we do in the climate physics groups. Specifically, one of the things that I work with are climate models. This is how we figure out the details. So the next part of my talk is, okay, the big picture we've known for 100 years. How do we figure out the details? We use these physical climate models. What are they? Well, they're basically weather models, right? So each one of you has in their pockets a direct connection to an atmospheric model, to a numerical atmospheric model. Only we use these models, the weather models, to make predictions about 2 weeks into the future of what the weather is going to be in Urbana. Climate models are essentially weather models. We just run them for 100 years, 200 years. We've sometimes run them for 1,000 years to understand what the future is going to be. Essentially, what a climate model is a bunch of Fortran code. Yes, we still use Fortran. It turns out if all you want to do is you want to integrate the Navier-Stokes equations a couple of billion times, Fortran is still the fastest thing around. We run these things on big supercomputers. They can take up to 1,000 processors, and it can take us about half a year of simulation time to simulate the next century. They are some of the largest supercomputers in the world are used for these simulations. Right, so okay. What we basically try to do is we try to build a digital twin of the Earth, or at least of the processes that are relevant for climate. So this is the ideal climate model. I see a lot of you smiling, that's good. I teach Climate Change 101, Atmospheric Sciences 140. I showed this figure to my freshmen and made a reference to the matrix, and nobody got it. This is from the movie The Matrix. I think, so the ideal climate model would be a perfect digital twin of the Earth, or at least of all the processes that are relevant for Earth's climate. We're not quite there yet. It's still blocky. This is a reference that my undergraduates did get. Climate models are like Minecraft for climate scientists. We basically built a blocky, we would call it discrete, another synonym is digital, simulation of the Earth. Everything gets put on a grid. It's not always square. It can be hexagonal. It can be all sorts of other things. But first order, you can think of everything being put in these discrete grids. There's water here. There's deep water here. There's a tree here. And this is basically how we simulate Earth's climate. It's like a computer game for climate scientists. Right? So we make these blocky, discrete representations of the Earth, and we simulate physics on them. It's not very different from most other physical numerical simulations. For example, we simulate clouds. This is one of the big ones. So we make a grid. I press the button. Okay. There's a lot of, we make a grid, we press buttons, and nothing happens. Right, and then each grid cell, we assign certain quantities, right? There's perhaps the amount of liquid water or the amount of cloud in that grid. And if it's white, that means there's a lot of water. And if it's gray, that means there's only some amount of cloud. And if it's black, then there's no amount of water. And then at every grid point, we also know what the velocities are, right? So it's just a discrete representation of a fluid flow. And then we simulate the next second, and based on the velocities in every grid point, we simulate how many meters has the liquid water moved from one grid cell to another. It's essentially, if you've taken calculus, you might remember that a derivative, you can write it as a discrete limit of t at y plus 1 minus t at y over a difference, and then to get to actual calculus, you take the limit where delta x goes to 0. We don't take that limit. We can't actually take limits in the real world. We choose a very finite small value for these delta x's, and we approximate the actual continuous equations of fluid dynamics. And we take it to the next step, and then that allows us, based on where there's liquid water and what the velocities are, we can move the cloud around. Then we can recompute what the velocities are. There's a lot of other things that go in, the amount of water vapor, some of that water rains out, some more condenses. But this is the gist of how a climate model simulates the physics of clouds, for example. They do a pretty good job. If you put enough computational power, if you make the grid small enough, you can almost not tell that this is a discrete grid. Right? These look like clouds. We can do a surprisingly good job. This is a numerical simulation of low clouds close to the Earth's surface. Everybody with me so far? And that's what climate models are. They are digital, which means discrete representations of the world, not unlike SimCity or Minecraft or any other computer game. Most computer games have a physics engine, is what they call it. Usually it's used to simulate things like bullets flying into things and characters in the game jumping and falling. We use similar engines to simulate primarily the fluid dynamics of the atmosphere and the ocean, the physics of clouds, carbon emissions, all sorts of other things. This is Chicago. What do we simulate? Everything but the kitchen sink. I'm not actually expecting anybody or my students to remember this. The point of this is there's a lot of things. We try to put every process we think matters for climate. And a lot of the work that I do, I run these climate models. I don't write the parametrizations, is what we would call it, the representation of processes. I do a lot of work on trying to understand which processes matter, which processes are well represented, what else do we need to put in these climate models, what might we have put in that's wrong, and so on. We know how to do a lot of these processes. The real problem is it can get computationally expensive. As I've said, we can run these things for half a year to get us 100 years of simulation.
I don't see albedo in that.
You do.
Do I?
Yeah. So we don't simulate albedo as a specific quantity. It's an emergent quantity. We simulate clouds, we simulate ice sheets, we simulate the difference between places that have forest and places that have grassland, between water and land, and each of these surfaces has different properties in terms of how much they reflect shortwave radiation, and that ultimately determines Earth's albedo. So Earth's albedo is a property that emerges basically from the distribution, from how much land you have, how much water, how many clouds, how much snow, and so on. So just to recap, what these climate models are is a way to solve physics on a discrete, gridded representation of the Earth. This is a horizontal. There's also vertical dimensions. They calculate temperature, pressure, winds, humidity. We take a bunch of physical equations and we discretize them and we try to then advance the model one time step at a time, couple of hours or minutes at a time for 100 years, for 1,000 years to make a prediction of the future. We have one of the largest computers on campus right now, since after Blue Waters is down, the School of Earth Sciences Keeling computer cluster is actually one of the largest on campus, and a lot of what it's used for is simulations like this. Also weather. We do a lot of weather simulations there as well. I do want to give you a brief history of this. Right? This is the end goal. This is the end goal. Are we there yet? How close are we to that? The first proposal for an atmospheric model comes from 1922. Richardson is trying to forecast the weather tomorrow, so he does this discrete representation of Europe. All the physics was basically there. The only thing that were missing were computers. It takes him 2 weeks to forecast the weather for tomorrow. He has a better idea than doing it himself. This is Richardson Forecast Factory. It's a climate model. This is the Earth. These are grid cells on the Earth, and he's basically saying in each one of these balconies, there's a bunch of people that are doing calculations of fluxes and velocities and clouds and so on, and then they're talking to this central processing unit. I think he even called these computers. These were people that were computing things. And he says maybe someday it will be possible to advance computations faster than the weather advances. At this point, it takes too long to make these calculations. First computer, one of the first computers, ENIAC, 1950. One of the first simulations is a numerical weather prediction. Takes 24 hours to predict 24 hours. Still not good enough, but by this point, the writing's on the wall. Computers are going to allow us to do these things fast enough. Suki Manabe takes this is a GFDL, the Geophysics Fluid Dynamics Laboratory. They ran the weather prediction. That's where Suki Manabe did his first climate model simulations. And this is what the resolution starts looking like. Pretty far from the matrix. This is Europe, Greenland. There's no Iceland. There's no real British islands. This is in the 1990s. 2007, we're now at 110 kilometers, thereabout. You can start noticing a bunch of features. So we're starting to do much better. We're still pretty far from the matrix. The real problem is what we call subgrid scale processes. This is a picture of, in a weather model, this is a picture of a thundercloud. The scale is about 10 kilometers. This is what the grid cell of a weather model would be. you can't really simulate these clouds very well. Now we can get down to about 1 or 2 kilometers. All of this would be one number, right? We just can't make a grid cell fine enough to simulate a lot of these processes. This is what 100 kilometers of a cloud field looks like. This is basically one grid cell in a climate model. This would just be gray, and you'll just have one value for the cloud reflectivity and the cloud albedo and so on. It's the largest source of uncertainty in climate models. There's a lot of processes that we know how to resolve. I've showed you that simulation of clouds. We know how to solve clouds. It's just too expensive to solve it everywhere on the Earth for 100 years. Well, we can do it, but it's expensive. One of these is a satellite image. The other ones are simulations of clouds. I honestly forget which is the satellite image. I think it's this one. So we now sort of have the ability to run these models and resolve clouds, but this one took months to simulate 1 month. So we're still slaves to the engineering of these computer systems, and we still would like much more powerful computers in order to be able to do a better job.
Do you have hopes or anticipations of using quantum computers?
Not really.
No?
They're not, as far as I understand, and I really don't know much about quantum computing. Integrating Navier-Stokes equations is not really where quantum computers have an edge over classical computers. GPUs and machine learning, however, have shown a lot of potential to speed these things up. So that's sort of the route that the field is going, and that's where we think a lot of the hope is that machine learning and GPUs are going to allow us to make these things a lot faster. We call them digital twins. This is sort of as close as we can be. Climate models are not perfect. This is what predictions of sea ice looked like. These were made, I think these actually were made about here. They were predicting a slow decline of sea ice. These are, and the red are the observations. Sea ice has actually declined much faster than our predictions. So this is a case where our predictions were falsified. Turns out we didn't actually have good skill in forecasting things like sea ice. Temperature is easy. It's an integrative quantity of energy. Other things are much more complicated, especially things that involve phase changes, much harder to simulate. They're not perfect, but they're still pretty amazing if you look at some of the things they forecast. But again, the details do matter. I have, I think, 3 more slides, and I think I can take the time to do it. So a lot of what I work on is trying to use these climate models and compare them with observations and try to improve them in order to improve those predictions and try to understand some of the basic theory to see where the models don't do it right. But that's still very much in the fundamental science range. Ultimately, part of our duty is to inform policy. How do we do that? Well, the way it's been done mostly, and we're involved in some of this work, is, oh yeah, I forgot I want to show this. We want to inform policy, and it turns out we need to do that very specifically as long as we just provide the facts to the American people. One of my favorite cartoons, one of the few good things to come out of the pandemic. Yeah, we've been doing that for a long time. It doesn't work that way. So, policy, right? Let's say that what we're trying to do is we're trying to limit global warming. How do you do that? We've known this for a long time. We want to limit global warming. We know that we need to stop emitting carbon dioxide, but you can't just do that. It's expensive. So we have 2 options. Option 1 is make it a law. You just say, we got to stop emitting carbon dioxide. This is sort of what the Paris Agreement did. Paris Agreement is an international agreement that's aims to keep temperature below 2 degrees and endeavors to keep it below 1.5. Nobody's explained to me what the difference between aim and endeavor is. Sort of setting two targets, like let's try for 1.5, but if not, 2 degrees should really be where we stop. Turns out it's not actually legally binding. It's an international agreement. It's based on individually determined contributions. It works, but it's really hard to write laws that will really bind people and have them stop emitting carbon dioxide. The other option, which used to be the consensus in the American political system about a decade ago, this was something that both liberals and conservatives agreed on, that one way in the middle would be to use market forces. And the way to do that is to put a tax on carbon, right? It's expensive to stop emitting CO2, but there's also a cost associated with global warming. And we should find a balance between those, right? So that's the other part that's sort of the end goal for some of these simulations. Some of the things that we do here is financial modeling of climate risk. Basically, we want to understand this chain. We have a need for energy. We're emitting fossil fuels. We're increasing temperature, and that leads to some economic damages. The problem is, we only really feel what economists would call the private cost. For us, the only cost that we directly feel is the cost at the pump, right? And maybe some consequence of climate change, but really from that one car ride that we took, the amount of global warming that leads to is very, very small. The problem is that CO2 is a well-mixed greenhouse gas. Anything that we do affects everybody, but we only really feel this private cost at the pump of burning CO2. 8 billion people feel the rest of the cost. And even though that one car trip is small, if 8 billion people take that car trip and everybody feels the effects, then it starts adding up. So economists would call this the social cost of carbon, and that's what we're trying to estimate. What is the total impact of emitting 1 ton of carbon dioxide? So what we do is we get information, and by we I mean my research group and other climate scientists. We get information from energy modelers, social scientists about energy needs, burning fossil fuels, and then we say, if I burn a certain amount of fossil fuels and if I emit a ton of carbon dioxide in the atmosphere, what is the total cost to society? So this is a lot of how we use these climate models, at least in my group, in terms of, we work on improving them, and then in terms of how do we use that information, we use them to compute the temperature change that results from burning fossil fuels. And then we use other types of information to understand economic damages. This is a figure actually from a group in Chicago on the loss of GDP due to changes in mortality. Turns out there's a statistical value to human life. It's about $7 million. You can argue with economists whether that is an accurate assessment, but you can make calculations and say, if you look in the northern United States, less people are going to die due to temperature warming because there's fewer deaths due to extreme cold. So you get a negative number, which means a negative cost, which means there's an economic benefit. If you look in the south, heat waves are going to lead to increase in mortality. You have an idea of that sensitivity. You have an idea of how much temperature is going to increase. You have a price on human life. And you can calculate the loss of GDP due to changes in mortality. And ultimately, what you hope to get is something like this. The percent of GDP loss that is associated with a given change in global temperature. And we hope that you can use this to put a tax on carbon, to say, yes, I know that it only costs you $4 at the pump, But really, if you factor in all of the economic loss due to climate change, you should be paying a lot more for that. And that, well, probably not a lot more, but that would be what a tax on carbon would try to do, is we would try to make an estimate of these economic damages. These are fraught with assumptions, but it's really the best we can do. There was a Nobel Prize in economics awarded for basically this approach to Bill Nordhaus. Okay, so that's where we are. I'm going to leave with a parting thought, which is that, in my view, climate change is a failure of imagination, and it's a double failure of imagination. The wildfire example is the first one. We know that climate is going to change. We've known for a long time. We still don't know the details, and I think a lot of people don't realize just how bad certain things can get. You think of, oh, a couple of degrees of temperature change, how bad can that be? But when you think of how that interacts with an extremely complex socioeconomic system, it's really hard to game out and to imagine what all the consequences are going to be. So the deniers, the climate deniers, suffer from that failure of imagination, just how bad things can be. If you're a climate scientist on social media, whether it's Twitter, Blue Sky, Threads, Instagram, the TikToks, or whatever kids use these days, you'll find that you get hate mail from both sides now. You get hate mails from the deniers. Oh, you're trying to destroy the American way of life by telling us about climate change. And you get hate mail from what are called climate doomers. People that are telling you, why didn't climate scientists warn us of just how bad it's going to be? Like, we did warn you. And why are you hiding from people the fact that we're all going to go extinct in 8 years? It's like, we're not. It's gradual. It's bad. We can still prevent a lot of damages. Those people suffer from a second failure of imagination, which I think is best exemplified by my last two slides. This is, I don't know how old this is, there's a climate summit. What do we need to do in order to stop climate change? Well, energy independence, preserve the rainforest, green jobs, livable city, renewables, clean water. What if it's all a big hoax and we create a better world for nothing? It could have been the case. It could have been the case that in order to stop global warming, we really needed to do really drastic things. Like, we could no longer drive cars. There's no way to make cars that don't burn fossil fuels. Eventually, climate change would have gotten bad enough that we will eventually have to give up cars. And we still would have needed to act on climate change. But that's not what's happening. We're lucky. It turns out that a lot of the things that we do that we would need to do in order to decarbonize the economy are good things. Some of these externalities are positive. For example, when you burn coal, you don't just emit CO2, you emit a bunch of other stuff, primarily dust and aerosols that have very direct impacts on air quality and health. And by moving towards electricity, especially if it's renewable electricity, we don't only get the benefits of reducing carbon dioxide, we get all of the co-benefits of no more lung cancer, no more air pollution. There's estimates that just those health co-benefits, the reduction in particulate matter, PM2.5 pollution, basically think of the wildfires this summer, but dispersed everywhere because of traffic. The co-benefits to the health system from that, the amount of money that we save on treatment of diseases caused by air quality, that amount of money might be larger than what it would cost us to switch to renewable energies. Those numbers are still up for debate, right? And not everybody benefits from that. If you've made a fortune by burning fossil fuels, you don't benefit. But in terms of the social cost, a lot of these additional effects might be positive. So That's the second failure of imagination. It's actually probably going to be much easier than we thought, and it's going to be a much nicer future in which we have better public transport, we don't have all these air quality issues, we don't have all of these additional things that come with burning fossil fuels. This is what makes me optimistic. This is my last slide. This is worth taking a minute on. This is the annual photovoltaic additions. Historical data versus the International Energy Agency's World Energy Outlook predictions. The International Energy Agency is a group of quote-unquote serious people, energy companies, economists, government agencies, that get together and try to understand where is the energy market going. And every year they issue a World Energy Outlook. And what this guy did was he looked at their predictions from the past, and they look very different than the climate scientists' predictions. Let's take, say, 2010. In 2010, the International Energy Agency, having noticed that photovoltaic additions had been growing, so people were putting 5 gigawatts of solar in 2007, 20 gigawatts of photovoltaics in 2010. They kept growing, and they'll say, actually, it's going to go down. People are going to put fewer photovoltaics next year. This red line is what they were predicting in 2010. They were predicting a decrease in the number of photovoltaics. This is what actually happened. It keeps going up. And somehow they keep doing it. Right? You're here in 2015, you've missed your mark every single year. You've predicted a stagnation in the growth of solar. Every single year you've been proven wrong, and you still say, actually, no, people are going to put fewer photovoltaics in the future. And it keeps going. This figure is from 2017. It's somewhere around here now. Right? Photovoltaics have been, not just the total amount, this is just the additions. So the number of solar panels that people are putting has been growing exponentially, and a lot of the players in the energy industry still sort of can't believe it. So that's sort of, again, that second failure of imagination. We have started doing things, and it might be easier than we think to do this. Renewables are getting cheaper, they're cleaner, people are much more educated on the benefits of renewables, on the dangers of air quality. So I'm cautiously optimistic that we can do something about it. That's it. That's what I came to tell you about. We've known about global warming for a very long time. We still don't know enough about the details in order to make the kind of predictions that we need for people to adapt and respond. We're getting there, but there's also reasons to be optimistic in the long run for me. Questions? So the question is, remember Suki Manabe's paper was temperature change under a stable relative humidity profile. So the question is that assumption of a stable relative humidity accurate? And the answer is, to the best of our knowledge, yes. The key is its relative humidity, which is the fraction of water in the air relative to how much water the air can hold. Clausius-Clapeyron, this famous relation in physics, says that as the air gets warmer, it can hold more water. This is why your house is very dry in winter. The air outside is very cold, so it can't hold more water. So even if the air outside is saturated, it holds as much water as it can, once it goes inside and it warms up into your house, all of a sudden it has very low water relative to how much it can hold. So it feels very dry. It sucks up water from your clothes, from your skin, from everything else. So as the atmosphere warms, there is more water. So the total amount of water vapor does increase. That's what we would call the specific humidity. So that does go up. What we think, and that really is a climate model result, is that the relative humidity stays the same. So the air can hold exponentially more water in total. The saturation capacity grows exponentially. The fraction of that is actually in the air stays constant. So the actual amount of water in the air does go exponentially.
Doesn't it also carry a lot more energy into the atmosphere?
Yeah, there's a lot more water. Water has a lot of latent heat. There's a lot more energy. And we think that has the potential to make hurricanes stronger. We have a prediction that hurricanes overall are going to get stronger. We don't know if they're going to get more frequent. We don't know where they're going to move. But in terms of total strength, yes, and that is the fundamental reason. Why does relative humidity stay constant? It's complicated, and it seems to be a bit of interplay of a lot of different things, of atmospheric circulation. Air rises and it precipitates and it stays fairly saturated near the surface, but because it rises up in the colder atmosphere, it rains out, and then when it comes back down, it's dry. And overall, all these things tend to lead to a fairly constant relative humidity. It's an open theoretical question whether there's a fundamental reason why relative humidity stays stable, or if it's just cancellation of different factors. It's a very good question.
Could you try to explain, please, what Navier-Stokes equations are in layman's terms?
Oh, they're just the equations, sorry. They're just the equations that govern the flow of fluids. They are one of the most infamous equations in physics. There's a quotation by, I don't know who said this, that when I die and meet God, I hope to ask him two questions. The first one is why quantum mechanics? The second one is why turbulence? And I'm really hopeful about getting an answer to the first. Navier-Stokes equations are the equations that govern the full turbulent flow of fluids. They're notoriously hard. Mathematicians don't really know if our current formulation of them even have a formal mathematical solution. There's like a $1 million bounty if you can prove that the Navier-Stokes equations can be solved. Meanwhile, we're just integrating them happily in Fortran, not worrying about whether or not we're allowed to do that. So yes, they're the equations that govern the flow of fluids.
I remember years ago seeing a documentary that claimed that the cost in traditional resources to run solar and wind farms exceed the benefit from these farms. Is that true today?
No, but that used to be true for a long time. That used to be true for a long time, right? When Jimmy Carter put solar panels on the White House, he was sort of laughed out of the presidency. It was much more expensive to build them than the lifetime benefit that they provided. That's true of a lot of things. The first cell phones were these giant, massive, blocky things that had about an hour of battery. And they were so inconvenient that almost nobody was using them. People weren't building solar panels back in the day because there was an immediate economic benefit. It was because they had enough vision to realize that at some point the technology is gonna get good enough that it is going to be economically advantageous. Electric cars, the first electric cars, the first Teslas, the first Karmas, they had 10 miles of range and cost $200,000, and only a few people can afford them. So that's oftentimes true of a lot of things. The reason I'm lingering on this point is because it's important that people still do that. It's important that people still see the benefit of buying an electric car when it's more expensive and drives less than an internal combustion engine, because it will advance the technology. There's people that electric cars are still fairly expensive. They're getting cheaper, especially if you factor in the lifetime cost of fuel savings and the fact that they're much cheaper to maintain, but there's still a big upfront cost. And a lot of people are buying them not because of the direct private cost, but because of the social cost. They're realizing that by doing that, I'm helping prevent global warming. So this figure, now, this exponential growth, yeah, solar panels are cheap, they provide cheap energy, they make much more economic sense than coal. At least now. There's a question of, well, if we have all solar and all wind, then there's issues of variability. So to get there, we also need to figure out storage and other things. But right now, it's cheaper to add a gigawatt of solar than a gigawatt of coal. Here, it wasn't. The people who were putting up solar panels here were doing it because they cared about the environment. And the benefits weren't just the fact that they were putting up a solar panel instead of buying coal electricity, or they were buying an electric car instead of buying an internal combustion engine, and they emitted less. The biggest benefit was they basically supported the advancement of these technologies. So I really am thankful for the people that were first movers on these technologies, because they realized the longer-term benefits of what they were doing. I want to take another question.
Yeah, do you think you'll live long enough where the technology will catch up to where you want to make it, to be able to, for you to make the predictions you'd like to on climate?
I think it depends how much I exercise and how well I eat, right?
For how long? Maybe 10 years?
Probably 20, 30 years. I mean, there's always better predictions you can make, right? You will not gonna get to the matrix anytime soon. But I'm hopeful that we're close to the edge of another big advancement in these computer models. They've sort of stagnated for about 20 years. I mean, they've gotten better, but the rate at which they've gotten better has not necessarily kept up with, say, Moore's law for how fast computers have gotten. And part of that is if you want to double resolution, well, you have to do it in 3 spatial dimensions and 1 temporal dimension, so it's like 8 times as much. But between a combination of GPU, machine learning, some other fundamental physical breakthroughs, and interest from society in funding us, there's hope that we are actually going to build much better models over the next 20, 30 years that are going to be able to give us much more useful information on things like wildfire, floods, heat, drought, and so on. Actually, here at Illinois, we have the National Center for Supercomputing Applications. We have some of the best computer science and computer engineering programs. We have great numerical physics groups. There's a big group of us that are sort of trying to put together a next generation climate computer. Part of it is it costs money. It used to be the case 30 years ago that some of the climate model computers were the biggest ones in the country. I think it was the second biggest one. The biggest one was the Los Alamos computer that was doing Monte Carlo simulation of nuclear weapons decay rates. And I believe the National Center for Atmospheric Research's supercomputer was the second largest supercomputer in the US. No longer the case. So the investment hasn't kept up with the rest of the computer science. But I'm hopeful that there's more interest now to put resources in, and we've had some breakthroughs that we might be able to make much better predictions in the next 10, 20, 30 years. A lot of it depends on resources, honestly. It takes not just climate scientists, it takes software engineers, it takes computer programmers, it takes a lot of people to put together one of these things. We're trying to do one here. We hope to become leaders in that. You had another question?
I was going to say the exponential increase in solar panels, et cetera. It's my understanding that life expectancy is somewhere around 25 years. And so all these solar panels being put up today, 25 years from now, what's going to happen to those? And can they be recycled? And the cost of it has to be figured in the overall cost, et cetera.
I don't know the details of that, but when I say that solar panels make sense over their lifetime, those things are factored in. The worst case scenario, have you ever taken the city of New Orleans from Chicago to Illinois? You know the song, City of New Orleans? You take the train from Chicago to Urbana, there's giant car lots just full of old cars that we're not recycling. So worst case scenario, it's not going to be worse than what we're doing with that. The coal industry, they leave giant scars in the environment wherever they strip mine for coal. So yeah, there's additional costs to that. If you integrate over all of them, they're still better. Do we have time for? I'm happy to keep taking questions. It's up to you.
We could probably have people come down to join.
Okay. You can. I'm going to stay here for a few more minutes. And
Is it still worth seeing Al Gore's An Inconvenient Truth over the Matrix?
yes.